Welcome to this lesson on the second-order condition, also known as SOC. In the next few minutes, you'll learn how to use the second derivative to determine whether a stationary point is a local maximum, a local minimum, or neither. Before applying the second-order condition, we first identify a stationary point, creating either a local maximum or a local minimum. To find these points, we begin with the first derivative. Start with a function, written as y equals f of x. Differentiate the function with respect to x to obtain the first derivative. This derivative helps us locate the stationary points. Next, set the first derivative equal to 0. Solving the equation f prime of x equals 0 gives the stationary point, where the tangent to the curve is horizontal. Now differentiate the first derivative one more time to obtain the second derivative, written as f double prime of x. The value of this second derivative tells us the nature of the stationary point.
If the second derivative is greater than 0, the curve is concave upward. This means the point is a local minimum, reaching its lowest value.
If the second derivative is less than 0, the curve is concave downward at the stationary point. This tells us the point is a local maximum, because the graph reaches its highest value. If the second derivative equals 0, the second-order condition cannot determine the nature of the stationary point, such as the first derivative test or higher order to classify the point. Now let's apply everything we've learned using a simple example. Consider the function y equals x squared minus 4x plus 1, whether it is a local maximum or a local minimum. The first step is to differentiate the function. The derivative of x squared is 2x, the derivative of negative 4x is negative 4, and the derivative of the constant 1 is 0.
Now set the first derivative equal to 0. Solving 2x minus 4 is 0 gives 2x equals 4, and dividing both sides by 2, this is the stationary point where we'll apply the second-order condition.
Next, differentiate the first derivative one more time. The derivative of 2x is 2, and the derivative of negative 4 is 0. Therefore, the second derivative is simply 2. Now we can apply the second-order condition.
Let's verify our answer on the graph. The curve opens upward, and the stational 2 is the lowest point that the stationary point is a local minimum because the second derivative is positive.
Here's a simple way to remember the second-order condition. If the second derivative is greater than 0, if the second derivative is less than 0, the graph is concave downward, a local maximum. Let's summarize the second-order condition. If the second derivative is greater than 0, the stationary point is a local minimum. If it is 0, the test is inconclusive. And whenever you solve an optimization problem, follow these 5 steps. Find the first derivative, set it equal to 0 to locate the stationary point. Find the second derivative, evaluate it at the stationary point. And now it's your turn. Pause the video if you need more time. For the function y equals x squared plus 6x plus 5, find the stationary point. Let's check the solution. The first derivative is 2x plus 6, gives x equals negative 3. The second derivative is 2, which is greater than 0. If you reach the same answer, great job!
Like, comment, and share this video. Subscribe to UNIC EDU for more easy mathematics lessons. See you next time.